Hello and welcome to another Ginger Mathematician video. So today we're going to go through all of A-Level Maths Paper 1, Connected Rates of Change, also known as Related Rates of Change as well. And if you're interested in a Ginger Mathematician mug, so I've got it here, right here, then of course just check out the tagged item down below. Right, let's get started. So we have the volume of a large circular mound of iron ore, radius r meters, is modelled by the equation here. For r is greater than or equal to 2. And iron ore is added to the mound at a constant rate of 1.5 cubic meters per second. Notice units are really important, just like physics here, because that's going to help us construct our differential equations. Now, find the rate at which the radius of the mound is increasing at the instant when the radius is 5.5 meters. So, lots of important information here. The first thing we need to work out is what rate are we looking for here? Well, we're looking at the radius, which is r. So we're going to be looking at the change in r and how that's increasing. So as soon as I say the word increasing, that's going to deal with time here. So essentially we are looking for dr by dt. So that's what we're looking for here. That's our kind of question mark. And we want to find out that derivative at the value of r is equal to 5.5. So that's what we're looking for here. But let's look at what information we have. Now, first of all, we have this formula here. So v equals 3 over 2, r minus a half all cubed minus 1. So we have v in terms of r here. So we could actually work out at some point dv by dr. We've also got this extra information here as well. So iron ore is added to the mound at a constant rate, got that keyword rate, 1.5 cubic meters per second. So that's a volume, and the second is a time. So we're told here that dv, the change in volume, over time is equal to 1.5. Okay, so I've got 3 bits of information. That's usually enough for these kinds of related rates of change question. The first thing I'm going to do here is actually work out another derivative from this information. I'm going to work out dv by dr, because we have v and r in the equation. If I differentiate this, again, you should know these rules really well by now. We take the 3, we bring it to the back. So 3 over 2 times 3 is 9 over 2. If we derive the bracket, notice we just get 1, so that doesn't change anything. So we can still leave this as r minus a half, nothing comes to the front here. And we reduce the index by 1, that gives us a 2. Remember, if we differentiate minus 1, that goes to 0. Now we're going to set up our chain rule so we can actually work out this dr by dt. So dr by dt is equal to, and then we need to match essentially these two derivatives so we can cancel out, in other words, the dv. So the way I'm going to set this up is I'm going to set this up as dv by dt times, I'm going to flip this dr by dv. Essentially kind of unsimplifying a fraction. That's kind of the way, because if I cross both these out, I'll be left with dr by dt. So if dv by dr is this, then dr by dv, if I flip it, is just 1 over 9 over 2 r minus a half all squared. So now I pop in my two derivatives. So let's get the highlighter. So dv by dt is equal to this. dr by dv is equal to this fraction here. So if I multiply the two things together, I get then 1.5 over 9 over 2 r minus a half all squared. So that's my derivative of what I'm looking for, the rate of change of the radius with respect to time. However, we want to work this out at 5.5. So when r is equal to 5.5, our derivative at that point, so r equals 5.5, we just substitute 5.5 for r, so we get 1.5 over 9 over 2, 5.5 minus half, weird mixture of fractions and decimals here, and squared. So let's put this in the calculator and find what it is. So make sure you've got any calculator to hand, it doesn't have to be graphical. So we have 1.5 over 9 over 2, so that's 4.5, brackets 5.5 minus a half, 0.5, Like things either decimals or fractions, don't like mixing here. And then we're squaring, so if we work out that answer, we get this 0.0133. So 0.0133. Let's think about the units here. Well, the radius is increasing, so that's in meters, and then the time taken is in seconds. So we're going to have that in meters per second for our 3 marks. Now, part B is a very typical follow-on question. So now we need to find the volume of the mound at the instant when the radius is increasing at 0.1 meters per second. So essentially, they're giving us the information of dr by dt. They've told us at a different time this is equal to 0.1. We also know what dr by dt is equal to. We worked this out in this part of the question. So the 0.1 must be equal to the fraction down below. So this is equal to 1.5 over 9 over 2. R minus, I think it was a half, wasn't it? Yep, R minus a half, all squared. So essentially, by using the information, we're told that derivative that we worked out here is equal now to 0.1. This is essentially a fairly nice quadratic to solve here. So the way I'm going to do this, I'm going to speed this up slightly. I'm going to multiply by R minus a half, all squared on both sides, and I'm going to divide by 0.1. So if I do that process, this comes up here, so we get R minus a half all squared is equal to 1.5 over 9 over 2 times 0.1. So I'm kind of doing this in one stage rather than two, but you could always do this in 2 separate stages. If we work out what's on the right hand side here, I'll do this quickly here. So 1.5 divided by 4.5 times 0.1, that gives us 10 over 3. And actually this is in a very nice form to solve this quadratic quite quickly. So what's the opposite of squaring? Square rooting on both sides. So this cancels, giving us r minus a half. And then we get plus minus the square root of 10 over 3. And then we want the r on its own. So we get r equals a half plus or minus the square root of 10 over 3. Now remember, r, we're told in the question, needs to be greater than or equal to 2. So we need to take the positive version only. So a half plus the square root of 10 over 3. We haven't finished the question here because we need to work out the volume. Now remember, we had that formula right at the start. So this one here. So 3 over 2 r minus a half all cubed minus 1. Make sure you use the right formula here. And then we just substitute it in. So we do 3 over 2. And we have our answer from before. Kind of looks a bit ugly, but your calculator can do a lot of the hard work for you here. All cubed minus 1. So let's pop this in. Again, it's good practice for us to do this together to make sure that we are putting in all the brackets in the right places. So we have 1.5. Then we have our answer from before, which was 0.5 plus the square root fraction button 10 over 3, close bracket, minus, oh, we're in the square root, this is why you have to be very careful what you're doing here. Let's actually bring that bracket out here. There we are, that's a bit better. Okay, perfect. So we have minus 0.5. One of the key skills on the course is just making sure we can use the calculator correctly. Now we have a cubed, don't forget that. And then finally we have minus 1. So we pop that in. We get it in some strange third form, but we've got the SD button. That is the magic button. And then we get 8.128. And rounding to 3 significant figures, we get 8.13. And we're doing this in volume, and we're working in meters, so we have meters cubed to 3 SF for all 3 marks. Okay, so you can have a look through the mark scheme. Notice You have to have the correct working here to get the 8.13. You can't just like guess it or do a trial and error method. They need to see this related rates of change process. Okay, on to our next question. So a large industrial water tank is such when the depth of the water is x meters, so we're using x for depth here. The volume is equal to this formula, so let's write that down. So we have V equals 243 minus the third, 9 minus x all cubed. Water is being pumped into the tank at a constant rate, magic word, constant rate, of 3.6 cubic meters per hour. So that means then the volume with respect to time here, that's going to equal 3.6. So I'm just writing down the key information. We want the rate of increase from the depth of the water, so we're looking at x here, when the depth is 4 meters. Again, we're looking at the rate of increase, that's time involved, so we're looking for dx by dt at when the depth is equal to 4. Okay, we do this in a very similar way. First of all, we take the function that we have and derive it, so we work out dv by dx. Now 243 looks scary, but if we differentiate a constant, it goes to 0. So we're just focusing on here. So we take the 3, bring it to the back. That gives us then minus 1. We have the derivative of the bracket. Be careful with that. So that's also a minus 1. And then we take the bracket and reduce by 1, so down to squared. So we actually get a positive 9 minus x squared. Biggest mistake students make is they forget to derive the bracket as well. That's important. Now we want to work out dx by dt at x equals 4. Again, we set up our chain rule here, so we get exactly what we want. So we have dv by dt multiplied by dx by dv. So notice, like in the last question, I'm going to flip this to give me the dx by dv. So we have 3.6, and then in below we have 9 minus x all squared. And we want to work out this derivative at x equals 4. So when x is equal to 4, our dx by dt at x equals 4, that's equal to 3.6 over 9 minus 4, that's 5, so we get 5 squared. And so we do 3.6 divided by 25, and that's equal to, I'm going to leave it as a fraction, 18 over 125. Notice we've been working in units of meters, and we're working per hour. Now, this is where it's a 5-mark question here, so that should tip you off. The previous questions were only 3 marks, but notice we need the answers in centimeters per minute. Very sneaky. We didn't really talk about the units here, but here we've got meters per hour, and we want to convert that to centimeters per minute. So when you think about what we're going to do to the units here, so in order to get this unit, we need to go from meters to centimeters, so I'm going to times by 100, and then to go from hours to minutes, we need to divide by 60. So very sneaky. We take our 18 over 125, we times by 100, divide by 60, and then we get our final answer as a decimal of 0.24. So units are really important. That's why I make a big effort about it, particularly in the first question and this one as well. Notice which unit you need your answer in. Lots of students will lose marks on this, whereas hopefully in the exam you will definitely not. So this is the answer here, 0.24. And being very careful. I think you lose only 1 mark here, so that's not too bad, but you want to be getting all those marks. On to question 9 here. Again, similar kind of question. So water is poured into a tank at a constant rate. Boom, boom. Got our word here of 500 cubic centimeters per second. So that means our volume, so dV by dt, that's equal to 500. You should always check all the units are the same, but generally they won't trick you on that. Notice the unit here is the same as this unit. So the depth of the water in the tank t seconds after filling is h, so that's our depth, not x this time. When the depth of the water is h centimeters, the volume is given by that formula. So let's write that down. So 4/3 25 plus h all cubed minus some big number that we don't really have to worry too much about. Perfect. I'm looking for the rate at which h is increasing at the instant when h is 10. So we're looking here for dh by dt, the change of the height of the water, at the value where h is equal to 10. Okay, same procedure as what we did before. First of all, we differentiate this function, so dv by dh, and we take that 3 and bring it to the front. So that gives us 4/3 times 3, which is 4. Differentiated bracket doesn't make any difference this time, we get just a 1. So then we just reduce the index by 1. Notice the constant just disappears at this point. And if we use the formula we used before, so you're getting lots of experience at using this. So we have dv by dt multiplied by dh by dv, this flipping of this particular differential. And if we do this, we get 500. Notice the questions are usually in the same kind of structure here, plus h all squared. Now we want h is 10, so when h equals 10, our derivative here at h is equal to 10 is 500 over 4 lots of 25 plus 10 all squared. Again, we just pop this into the calculator. So 500 divided by 4 times 35 squared, and that gives us then 5 over 49. Actually, I like them as fractions, but the mark scheme prefers them as decimals. So 0.102. Let's think about the units here as well. So we have centimeters and time here is in seconds. So we have centimeters per second. Notice I'm just looking for this. I'm looking for this to help me with my units here for the particular rate that we're looking for. On to question B, again, similar to the first question we did. At another instance, the rate at which h is increasing is this instead. So we're now told that our dh by dt, which is what we worked out before, but for a different moment, is now 0.075. Notice we already worked this out in this first part of the question. So we know our new rate must be equal to this. So equal to 500 over 4 lots of 25 plus h all squared. Double check I've written that correctly. That's important. And now we just got a quadratic to solve here. So again, I'm going to do this in one step. I'm going to multiply by 25 plus h all squared and divide by 0.075. That's going to give me then 25 plus h all squared is equal to 500 over 4 times 0.075. So let's work out the right hand side here. So 4 times 0.075 gives us 5,000 over 3. So we need to solve this. So opposite of squaring is square rooting on both sides. We cancel. This is the part where you can relax, just work through your quadratics. So we get the plus minus to square root of 5,000 over 3. We'll probably be taking just the positive here. Don't think it says that specifically, but again, we want a positive height here. And then we minus 25, so we have h equals minus 25 plus minus the square root of 5,000 over 3. So we only need to take the positive answer here. So minus 25 plus square root of 5,000 over 3. Yep, perfect. And that gives us 15.8248. Again, I'm not going to round this straight away because we want to work out the value of v, the volume here. So to work out the volume, we go right back to our first function here, so this one here. So we want 4/3, 25 plus this 15.8 that we worked out before, cubed minus 62,500 over 3. Double check everything is there. Okay, so I will pop this into my calculator. So if I do this, again, we'll get to our final answer rounded. Again, you can do this at your leisure and check that I've got everything correct here. This will give us then 69,900. What's our units here? Well, we have cubic centimeters, so we want to make sure we have the same units down here as well to get our final answer. Okay, so you can go through the mark scheme here and check all the working that you've done so far. So, slight twist to the videos that I've done before. So here's another question for you. So this is question 3. What I'd love you to do is in the comments, can you tell me what the solution to this question is? This is really showing your knowledge from what you've done before. Can you apply it to a slightly different question here? And if you need to revise all things A-Level Maths Paper 1, then do check out the video right in front of you.